Let's take a look at exponential functions, what the functions look like, as well as what the graphs will look like. So today we're going to look at how to graph exponential functions. We're going to find the domain and range, and we're also going to find asymptotes after we understand what they are. So exponential functions are where the variable is in the exponent instead. So you might have a number here, and then you might have the variable up here. Now there's other things you could have in the exponent, like for example, you might have numbers and things up there as well. But for simplified purposes, let's just call it y equals a to the x. Now y equals a to the x, where x is positive, is going to be growth, exponential growth. All right, and these graphs look like this. Exponential growth looks like that. Whereas if you have a negative exponent, so if it's negative x, for example, this would be exponential decay. Decay. Another way to spot decay, by the way, so let me write or if a is a fraction where it's between 0 and 1. So if a is a fraction, then that causes exponential decay. Now what does decay look like? Well, exponential decay looks like this. It's going to be coming down from really big, and then it'll be getting smaller and smaller and smaller. Okay, so this is decay, and up here we had growth. All right, now what about the domain and range of these things? Now domain is how far left and how far right they go. Domain on all exponential functions is going to be all real numbers. Okay, exponential growth and decay, the domain is all real numbers. Now what about the range? The range. So the range on these is generally, the range would be the y values are going to be bigger than or equal to some horizontal asymptote, here. So generally there are horizontal asymptotes. In my examples that I drew off to the right, you see how they are the x-axis, so that's y equals 0 in both cases. So it's just going down like this. It just keeps going down, gets closer and closer to that x-axis, but never quite gets there. So usually it is 0, but it can be a horizontal asymptote, as we'll see in some of the examples down below. All right, moving down here in the notes, it says, an example, determine if the functions are exponential. So, do we have a variable in the exponent? Yes, we do. Do we have a numerical base? Yes. And then we've got vertical shift is all that does, vertical shift. Let's write that down, vertical shift of the graph. So yes, this is exponential. We're going to look at the graph on this here in a moment. So let's go to the right here. Is this exponential? Do we see a variable in the exponent? No, the variable's the base. So no, variable is the base and not in the exponent, okay? So exponentials have a variable in the exponent. Over here to the right, boy, this looks like a mess, doesn't it? Let's go through our checklist. Is the variable in the exponent? Yes, it is. Is it a numerical base? Yes, this right here is the numerical base. And then there's some other stuff in the problem, and all these things do is move the graph around. So this 4, this actually shifts the graph up by 4. This makes it steeper, okay? And then the fact that this is a fraction, you remember what I said before? When the base is a fraction, since 0 is less than or equal to or less than 1/2 or less, which is less than 1, this is a decay problem. So if we were to graph this, it would be sloping downward like this. Okay, decay looks like this. So we'll figure out the exact graph here in a moment. So The next problems say graph the exponential function on Desmos and determine the domain and range. Note any asymptotes. All right, so if you go to Desmos and graph this, here's what you're going to see. 2 to the 0 power is 1. So what that means is when 0 goes in, 1 comes out. So that's important for you to note. The y-intercept is when x is 0. So I put a dot right there. Now what about when 1 goes in? What is 2 to the first power, right? Because we're putting 1 in right here. So 2 to the first power means 2. So 1 comma 2. So we go over 1 up 2, and we're starting to see what this might look like. Now we said on the previous portion of this video that we have horizontal asymptote, and since there is no vertical shift at all, we know that there is an asymptote, and it's horizontal at y equals 0, and that's over here. Okay, so that's this guy right here. That's called a horizontal asymptote. This thing is getting really close to the x-axis, but never quite gets there, never crosses it. Okay, let's look at this. Oh, I'm sorry, we forgot to say domain and range here. So the domain on this one is all real numbers because it exists everywhere left to right. That's why it's all real numbers. Now, what about the range? How low does it go? Okay, so y is always bigger than 0. It never actually gets to that asymptote, so it's bigger than 0. Now, interval notation form is where you write the smaller number first, and then it goes forever and ever. So this is called interval notation. You probably remember that from earlier in the course, interval notation. So that's important to note. Now we're ready to go over here. This is going to be decay since we have a fraction for a base, a fractional base. So as I'm graphing this, I know that the graph is going to be going down like this. Now, let's figure out our y-intercept. This plus 1 shifts the graph up by 1, by the way. So if you want to just start there, you could even start there. You could go up by 1 and put a horizontal dashed line there, because that is the line y equals 1, and that's the horizontal asymptote. Because that's what these things have. These always have horizontal asymptotes, and this plus 1 at the end simply shifts the asymptote up. Instead of being on the y equals 0, it's at y equals 1. All right, now it is decay. We know that, but let's figure out the y-intercept. So when y is 0, let's plug this in. When x is 0, anything to the 0 power is 1. So this is 1. Anything to the 0 power is 1. Say it with me. Anything to the 0 power is 1. So 1 plus 1 is 2. Okay, 1/4 to the 0 power equals 1, exclamation point. All right, so you might want to put that in your notes, that note, anything to the 0 power is 1. You plug it in your calculator. So 0, 2 is right here. That's at 2. Now let's plug 1 in there. If you plug 1 in, you get 1.25 because it's going to be 1 plus 1/4. So that is a little bit lower, isn't it? So over 1 up 1.25, and you can see how it is decay after all. So let me graph the decay function. It's going to be getting really close to that horizontal asymptote. This is exponential decay. So what is the domain and range? Again, domain is all real numbers, or if you want to write it interval notation, it would be -infinity to infinity. The range here is y is always bigger than 1, or we would say 1 and above. 1 comma infinity, that's the interval notation for above 1. All right, we got one more example over here. So this would be growth because 7 is bigger than 1. Okay, so this is growth. So this -3, this is a downshift by 3 as far as that asymptote goes. So we could go down 3 and put a dotted line there. Not a bad idea to write y equals -3, and that's your horizontal asymptote. That's your horizontal asymptote here. Let's figure out that y-intercept, because that's always a pretty easy one to do. So when you plug 0 in, you get 7 to the 0 power. That's 1. 1 times 2 is 2. So this whole thing is 2. 2 minus 3 is -1. So 0, -1 is where the y-intercept is. Now I always like to plug 1 in to get another point. So 1 comma 7 to the first power is 7 times 2 is 14. 14 minus 3 is 11. Oh my goodness, this is really taking off. So at 1, it's way the heck up here at 11. So this gets really steep, and that's one of the things I want you to realize about exponential growth and decay is that they really do get steep pretty quickly. That's the whole point of an exponential. It talks about growth and how fast it can happen. All right, so what about the domain and range here? Again, the domain is all real numbers. The range would be y is always bigger than -3 this time, because remember that was the horizontal asymptote. So we would write -3 comma infinity. That would be a way to write the range. So there's the 3 graphs of some exponentials. So horizontal, vertical asymptotes, those are always going to be y equals something for the horizontal. Okay, and it's often 0, which is the x-axis. Okay, but it doesn't always have to be. You saw up here, the first one was 0. The second one was not, remember, right? The asymptote was shifted up by 1. And then on the right here, on this last graph, the asymptote was shifted down by -3. Now, what about vertical asymptotes? Have I talked about that at all? No. There's none. There are no vertical asymptotes ever, ever, ever. Now, you might say, but wait, Mr. White, doesn't it get close to something here? No, it doesn't. All right, it will always be moving to the right. It will always be moving to the right. So it will always cut through any asymptote you try to draw. So no, there is no vertical asymptote. No vertical asymptotes. So then it says determine the horizontal vertical asymptotes of the graph, if any. So no verticals. Vertical was none. The horizontal, we saw it in the graph, didn't we? It was y equals 0. Vertical here was none. The horizontal, because of this +1, that shifts the graph up. So that simply makes the graph have a horizontal asymptote 1 higher than it normally would have. Normally it's at 0, but this one's 1 higher. And then remember what happened on this last one? We had vertical was none. And then the horizontal was y equals -3. So there you have it. We did graphs on exponentials pretty quickly, didn't we? And we also started to notating the horizontal and vertical asymptotes, which was none. So let's go back up here to the top. We graphed some exponentials. We understand what they look like now, hopefully. We also did domain and range. And we did vertical and horizontal asymptotes. So hopefully you feel like you've got a good primer on what these graphs look like. And good luck on your assignment. Okay, until next time.